Hello, everyone. Happy Friday or Tuesday or whenever you're watching this. We have a long weekend coming up, if you didn't know. So we have spent a good amount of time working on stoichiometry. At this point, I haven't had any questions from any of the virtual kids, so I'm assuming you guys are doing okay. The work that's been turned in has looked great. So just double check that you are always looking at the work after it's been graded. So if you go into the grades tab on Canvas, so if you go into chemistry and then you'll see grades on the left-hand side, you click on that and you can open up the assignment from there. You'll see any comments that I've left on it. So always be checking for that because I am frequently going through and leaving little comments if there's anything to say. But the stoic so far has looked really good. So we are going to keep on building with that and move on to limiting reactants today. Percent yield we did a little bit with in class with a lab, but we're going to really focus on that more next class with reaction efficiency. So today we're going to just really focus on the limiting reactants. So we're going to figure out in an equation which substance will be the limiting reactant. We'll be able to calculate the amount of moles or mass in grams of the product, or how many moles or mass of two reactants, and then which one is the excess. You guys will also be able to, we'll stop for there for today. So we're not going to get into theoretical and actual yield today. So we're going to start talking about limiting reactants. You might also see this as limiting reagents. It's basically the same thing. So you're talking about the things that you are starting with, not the products, but the materials that you're starting with, how much of that do you need, and then how much will be left over. So we know that reactions are rarely going to begin with exactly the required amount of reactants. So once one of the reactants is used up, no more product can be formed. Okay, so the difference between these, your limiting reactant is a substance that is used up completely and makes the reaction stop happening. So it limits the reaction. The excess reactant is anything that is not used up completely. So you can have more than one excess reactant, but your limiting reactant is going to just be one thing, unless you have two substances that will be used up exactly at the same rate. So in this example down here with the hamburger, okay, you have 4 buns, 6 pieces of cheese, 3 pieces of lettuce, and 5 burgers. So if we're assuming that we need one of each of these things to make one cheeseburger, which of these would be the limiting reactant? So if you're assuming you need like one bunch of lettuce, then yeah, the lettuce will be your limiting reactant because there's only 3 of them. So and to make complete cheeseburgers, you're only going to be able to make 3 because you only have 3 pieces of lettuce. So in the end, your excess, you're going to have 1 bun left over. You'll have 3 pieces of cheese left over and 2 burgers left over. So that's what we're going to be doing just with chemical reactions. Okay, so in this example, we have carbon plus oxygen yields carbon dioxide. So our mole ratios are going to be used to determine how many moles of each substance are required to make the products. So in an example, we have 5 moles of carbon and 10 moles of oxygen, which is a limiting reactant, and how much excess of the other will be left off. So the balanced equation at the top tells us that carbon and oxygen have a 1-to-1 mole ratio. So you have 5 moles of carbon, which is what's given in the question. So we're going to start with 5 moles of carbon. This also needs 5 moles of oxygen to react completely, right? So if it's a 1-to-1 mole ratio, if we start with 5 of these, we have to have 5 of these to make 5 of those. Okay, so if you have 5 moles of carbon, it's going to need 5 moles of oxygen to react to completion. If you've used up 5 moles of oxygen, you still have 5 moles in excess. Okay, so this picture shows this pretty well here. So we started with 5. These little dots are going to be the moles. These are each a mole. So we have 5 moles of this, 10 moles of that. We can react all 5 of these completely to make 5 moles of carbon dioxide, but then we're going to have 5 oxygen molecules left over because we're just not going to have enough carbon to react with it all. So an example of these problems, essentially what you're doing with limiting reactants is you're doing stoichiometry to figure out how much you can make with what you start with. And you're going to have to do that for all of the reactants involved. So you're going to pick a product to compare everything to. It does not matter which one you choose. So if you want to do the first one or the second one, doesn't matter. So in this case, we are comparing the reactant side to the product side. So for this problem, I went ahead and just picked silicon tetrafluoride, and we're going to have to compare both of the reactants to that to see which one is going to be used up. So according to the following equation, if 6 moles of hydrogen fluoride are added to 4.5 moles of silicon dioxide, which is a limiting reactant? Okay, so step 1, we're going to choose one of the products to work out in your calculation. This is arbitrary. It doesn't matter which one you choose. You just need a constant for comparison. So for this example, I'm going to use the silicon tetrafluoride. If you wanted to use the water, it would be the same result. It does not matter. So you can pick either one. It doesn't matter. So for this one, I told you which one I'm going to pick. We're going to use stoichiometry to determine how much the product you can make using the given amount. So in our question, it says we're starting with 6 moles of hydrogen fluoride, and we're also starting with 4.5 moles of silicon dioxide. So we're going to have 2 stoichiometry problems to compare these. So we need to figure out, starting with 6 moles of hydrogen fluoride over here, how much silicon tetrafluoride can I make? Because that's what I chose to compare it to. So then over here, we have to say, if I'm starting with 4.5 moles of silicon dioxide, how many moles of silicon tetrafluoride am I going to make? So this is a very simple conversion because we're just doing moles to moles. So if I start with 6 moles of hydrogen fluoride, here we are switching from hydrogen fluoride into silicon tetrafluoride. This is the mole ratio. So I got that from my balanced equation. Balancing equations is important. So I know my mole ratio is 1 silicon tetrafluoride for every 4 hydrogen fluoride. So I'm going to pop it in here and do the math to solve. So if I start with 6 moles of hydrogen fluoride, in this reaction, I can produce 1.5 moles of silicon tetrafluoride. Now on this side, we have to figure out how much could you produce with the silicon dioxide. So I'm starting out with 4.5 moles of silicon dioxide. That's what's given to me here. I need to convert that into silicon tetrafluoride. So that, again, will be our mole ratio. So anytime you're changing it from one substance into another, that's the mole ratio from your balanced equation. So we had 1 mole of silicon dioxide for every 1 mole of silicon tetrafluoride. I'm now going to do the math and figure out that I could make 4.5 moles of silicon tetrafluoride. Now, the last part is to figure out which of these is the limiting reactant, because that's what the question is actually asking. So we're going to analyze our results. The reactant that produces the smallest amount of the chosen product is the limiting reactant. The other one will be in excess. So in this case, using the hydrogen fluoride, we can only produce 1.5 moles of silicon tetrafluoride. On this side, using the silicon dioxide, we can do 4.5 moles of the designated product. So obviously, if we start with 6 moles of hydrogen fluoride, this is going to be the least amount of the product that we can produce. Okay, we cannot make any more silicon tetrafluoride than 1.5 moles with this given amount here. So our limiting reactant in this case is the silicon tetrafluoride, because we can only make 1.5 moles with this starting amount. Now, if we increase this to 12, could we make more? Yeah, but in this situation, you're in a lab and you only have 6 moles of hydrogen fluoride, so we can only produce 1.5 moles of silicon tetrafluoride. Okay, so it's a lot of steps, but it's nothing new necessarily. You're just comparing it to, you're just taking all of the reactants and comparing the product that you can make. Okay, so we'll do another example. How much excess reactant is left over? So it's the same problem. Remember, the original question began with 6 moles of hydrogen fluoride and 4.5 moles of silicon dioxide. The limiting reaction was hydrogen fluoride. Okay, so I put in the balanced equation again. So your first step is to say, using the amount of moles given from the limiting reactant, calculate how many grams of the excess reactant will be used. Okay, so we already know here that we are going to start with the 6 moles of hydrogen fluoride, and we're going to have to convert that into the other reactant, okay? So we knew that the hydrogen fluoride is our limiting reactant between the two, but we need to figure out how much will be left over. So we're going to have the 6 moles of hydrogen fluoride. We need to convert that into silicon dioxide. So we're going to use our mole ratio. We have a 4-to-1 mole ratio, and you're going to get 1.5 moles of silicon dioxide. We will subtract the amount of reactant produced from the amount given. Okay, so in the original question, you started with 4.5 moles of silicon dioxide. If you're going to use up 1.5 moles of silicon dioxide in this reaction, you're going to subtract them. So you started with 4.5 moles, you're only using up 1.5 moles. So you're going to end up with 3 moles of silicon dioxide of excess reactant. Okay, so here's another example. This one will be more similar to your practice problems and anything that we're going to do in a lab. So assuming we start with 20 grams of ammonium nitrate and 50 grams of sodium phosphate, you'll need to find the following. Which of the reactants is a limiting reactant? What is the maximum amount of each product that can be produced? And how much of the other reactant is left over after the reaction is complete? So in this case, you're going to start out with writing and balancing the equation. Okay, so you have this right here. We've written the equation and it is balanced now, okay? So we have to figure out first which of the reactants is the limit. So out of this equation, we have ammonium nitrate is one reactant and the sodium phosphate is the other reactant. Okay, so you're going to have two problems set up here, and we're going to have to figure out which is the limit. In this case, I went ahead and just chose sodium nitrate as the product to compare them both to. It doesn't matter. You could have chosen the ammonium phosphate. You would end up with exactly the same results, okay? So what you're picking to compare these two is arbitrary. It does not matter. So I chose this one because I figured it was less to add up. Honestly, that's the only reason I picked it. So in this problem, we're starting with 20 grams of ammonium nitrate. I have chosen to convert that into sodium nitrate just to compare the two. So here I'm starting with 20 grams of ammonium nitrate. I know eventually I need to change this into moles, so I'm going to bring down the grams of ammonium nitrate here. I added this up off the periodic table, so I had 2 nitrogens plus 4 hydrogens plus my 3 oxygens. That was 80.02 grams. The mass of this is equal to 1 mole. That is always going to be the same. 1 mole of anything is equal to its mass. So now I'm in moles, right? So moles of ammonium nitrate comes down because that has to be the path we follow. Now here is our opportunity to convert this from ammonium nitrate into sodium nitrate. So we're going to use the mole ratio from our balanced equation. So there are 3 moles of ammonium nitrate for every 3 moles of sodium nitrate. So 3-to-3 ratio. Now we are in moles of sodium nitrate because these ammonium nitrates have canceled. So 3 moles of sodium nitrate. Moles of sodium nitrate has to come down. We are trying to go all the way to grams here. So we're going to convert this back into grams. So same thing you did on this step, it's just flipped because now the moles is on bottom. So we have 1 mole of sodium nitrate is equal to its mass. Again, I just added this up from the periodic table. Now that you're in grams of sodium nitrate, you can solve this. So it says that we're going to get 21.24 grams of sodium nitrate using all 20 grams of ammonium nitrate to start with. That's great. That's a good first step. So the next step we have to do is the exact same problem, but with the other reactant start. So we know that we also have 50 grams of sodium phosphate. We are going to convert that into the same product as we did on the first one. So all we're really changing here is that we are changing this into sodium phosphate and then altering the ratios as needed. So 50 grams of sodium phosphate, I got that 50 grams from the question. Grams of sodium phosphate comes down. We're going to convert it into moles right here. So I added all this up from the periodic table. We got 163.94 grams. It's equal to 1 mole. So now we have 1 mole of sodium phosphate. Moles of sodium phosphate is the unit that comes down. Here's our opportunity to use the mole ratio and convert it into sodium nitrate. So we're going to use mole ratios from the problem. We have 1 mole of sodium phosphate for every 3 moles of sodium nitrate. So we're going to put that in. Now the moles of sodium phosphate have canceled. We're in moles of sodium nitrate, which we're almost there now. So moles of sodium nitrate come down. 1 mole is always equal to the mass if we're trying to get it back into mass here. So the mass is going to be the same from the first problem because we already added it up. And then now at this point, you're in grams of sodium nitrate and you can complete the math. So we know that the sodium phosphate will be in excess because we could have produced a whole lot more of the product using this much of this reactant. So judging off of this, you would choose the ammonium nitrate is your limiting reactant, okay, because there's not enough of it to produce as much as the other reactant, okay? So you are limited by this one because it's going to run out and the reaction will stop. So you can only make 21.24 grams of your product using this reactant, so that is the limiting reactant, okay? Next question is, what is the maximum amount of each product that can be produced? So we know that our limiting reactant is going to be the ammonium nitrate, okay? So you can't make any more product, you can't make any more sodium nitrate than 21.24 grams because we know that this is our limit, the 20 grams of ammonium nitrate, and that's all we have. So the maximum amount of product that we can make of this product, because we've already calculated it, is 21.24 grams. Now what we need to do is the exact same problem, except we need to figure out how much of the other product we will be able to produce using the same starting amount of ammonium nitrate. Okay, so in this problem, you're starting with 20 grams of ammonium nitrate. We already determined that that is a limiting reactant. So we're going to start with that again. So 20 grams of ammonium nitrate, grams of ammonium nitrate comes down. You have the mass of ammonium nitrate equal to 1 mole. Here, moles of ammonium nitrate has to come down. This is our opportunity to convert it into the other substance, so we're going to use the mole ratio. 3 moles of ammonium nitrate is equal to 1 mole of ammonium phosphate, so 3 to 1. Now we're in moles of ammonium phosphate, so moles comes down. We can set 1 mole equal to the mass of that substance and do the math. So in this equation, the maximum amount of each product that can be made starting with 20 grams of ammonium nitrate is going to be 21.24 grams of sodium nitrate and 12.42 grams of ammonium phosphate. The last part of this is a really involved question. So not every question will be like this in the assignment. How much of the other reactant is left over after the reaction is complete? Okay, so we've already done a little bit of work here. We know that we already know that the ammonium nitrate is our limiting reactant. So we need to figure out how much of the other reactant will be left over when we're done. Okay, so if we start with 20 grams of ammonium nitrate, we are going to convert that in the same fashion as the others into the other reactant at this point. So now we've done stoichiometry for all combinations of the limiting reactant and everything else in this problem. So we are going to convert this into the sodium phosphate, which is the other reactant, and figure out that you will use up 13.66 grams of sodium phosphate in this reaction. So if we started with 50 grams of sodium phosphate, and we're only going to use 13.66 grams of sodium phosphate, we're going to have 36.34 grams of sodium phosphate left over when we're done. So I know this has been a lot to process probably. We will spend more time on this next class. So if you're not quite getting it, don't panic. But please let me know immediately if this is just making no sense. Okay, so if we need to set up a Zoom meeting, we can. This is kind of the hardest point of this unit. Okay, so if it's not making sense, let me know. We can set up a Zoom. I can make another video with other examples. If you just need to see more examples, we can get on a phone call. You can come in, whatever. So let me know if you do need extra help with this. Don't forget to be checking your homework that's been graded for comments, and just let me know how you do on this. There's also a quizzes, so you need to complete the quizzes. That'll also give you just some more practice with these. The more you practice, the more comfortable you'll be, and the better you'll get at it. So hope you do well with these. Let me know if you need any help, and I will talk to you guys next time.